Hi everybody, my name is Jaanus Kääp, like it was told, and today I will be talking about corpus distillation and fuzzing. First a little bit about myself. Like I said, I'm Jaanus Kääp. I'm from Estonian company called Clarified Security. In there we mostly deal with training, and also we are doing red teaming and overall organizational stuff for cyber exercises, both in company level and international government level. Myself, I have developer background. I was web and native code developer for about 5-6 years before I moved to security. And I didn't bring out any certificates that I have, but I have found in past in web applications in Facebook, Adobe, Google, Spotify, Apple, some vulnerabilities. But we are not talking about web stuff today, and we are talking about fuzzing. And so first question, why this topic? The list there is a list of CVEs or a list of zero-day vulnerabilities that I've found with this method that I will describe. This is not total list. This is a list that has been a list of stuff that has been fixed in last about a year. So it has been quite successful. The number of CVEs behind Apple is because I don't have a lot of Apple computers to fuzz. This is the basis of the topic, why I'm talking about this. This method has been really successful in finding zero-day vulnerabilities in many native code applications. A little bit about what I'm talking about today. I will cover first the fuzzing basics, what fuzzing means. So everyone has the why fuzzed and found those vulnerabilities. And then I will give a quick look at the tools that I've written about if you want. And those tools are open source. Let's start. Vulnerabilities or some simple bug. I said automated way. Generates for either web application or for example document reader. It generates some PDF or doc or docx files. It executes them. Testable program for web services. You send some packages in this way. Give it as in. It opens this file. Special condition. That you start on the side of the room some computer and go back in a month or so and see what it has found. What you're trying to detect, well, it depends what you're testing. If you're testing some web application, for example, with something that you can recognize as cross-site scripting, or you want to detect has some SQL injection happened, or something like this. With native applications, it's in some ways more easier. You wait for patches, or more exactly, you wait for some exceptions, like access violation, depth violation, or some such behavior. If you're testing some, let's say, network service, because you do, or someone else can do, Word document reader just crashed. Services, it might be important. So it's highly target dependent what you're looking for. So input generation, based on generation, fuzzing has been have dumb fuzzing, which also applies to totally stupid random. We start with total stupid random fuzzing style. This means that you generate total garbage, total random stuff, and use it as input. You take it for random or wherever you and you put it to the file or send it to a socket. is that it's really easy to create. Like I have one-liners here that writes this totally random stuff to or something like that. Is that it almost never works. The parsers, document openers, and such are not method. Then all the PDF readers does at the beginning of starting to parse the file, they check is the first 4 bytes percent PDF. If it's not, it throws the file away and says it's corrupted. Now, if you generate totally random files like this, the probability that you get the first 4 bytes percent PDF is 1 out of 4 billion. So it takes some time to get past the first check. So it's not that useful. Then you have mutation-based fuzzing, which is actually a situation where you take a valid input. Let's focus for now on, because all the stuff that I found are in PDF readers or Microsoft Word readers or something like that. And let's take put this whole file. It goes for web services and other stuff. So, but from now on, let's talk only about files. You take some working file. For example, for PDF, you take some valid, correct PDF file, and you change something there randomly. You flip some bits. For example, you flip 0.1% of the bits inside the PDF file and run it. Doesn't do anything? Okay, revert the changes, make new changes. Does it happen? No. Then do it and do it. The special situations that someone made some mistake and stuff crashes. Now, like I said, pros of this is it's still easy to create. You just need to flip some bits on valid input. You don't have to know anything about the protocol. You don't have to know anything about the file structure. You don't need to know specification. You still get better code coverage than total randomness, because you get past the first checks, and most of the times the file that you generate, if you don't change every second bit, then the file is usually even correct in a most sense. So you get to is that it depends highly on the initial set of the initial files that you're going to mutate. If you have, for example, 4 PDF files that you start modifying, mutating, and all of them contain only code coverage, it doesn't cover, for example, parsing, tables parsing, all this kind of stuff. So it's important to have good initial set of files to start to mutate. Last type, which is generation-based or smart fuzzing. In smart fuzzing, you pretty much write editor, document editor, or something like this, because you actually implement the specifications of the input, either the file or the package or something like that. So you first have to understand all the specifications or some of those, then write and use randomly for PDF, for example, are several hundreds pages long. You have to read them and then write. It takes time. Secondly, if you have some program that doesn't that is handling, so it's closed source protocol or closed source file specifications, then you have to first reverse engineer the program that opens it to understand what the input is consisted of. And reverse engineering something, if you have ever done it, you know it's very time consuming. Reading assembly, not that. So what I did, first of all, I'm lazy, and based on that, I didn't want to write. I still wanted to find some vulnerabilities, so I didn't want to write the totally dumb puzzle. I choose mutation based, and I had a couple of computers laying around that I could use for constant fuzzing. So it was dumb fuzzing, but the mutational. So first question for me, if I start doing mutation-based fuzzing, is how to improve the initial, how to make it such that initial set consists as much functionality as possible, so you get best code coverage. For me, I use PDF, which was uncommon protocol for me. I know how PDF files, what they consist of. I might have broad idea, but I didn't know exactly. I haven't read the specifications. I even didn't care. But PDF was very common file type, and it has a lot of readers. So I choose PDF. And here comes in corpus distillation. Corpus distillation is a method of reducing the initial set of the inputs that you're going to mutate. At least in this context, it means that. In biology, it means something else. This is not important. What they need is a huge number of initial files. A huge number depends on the situation, what means huge for someone, but let's say you have 100,000 PDF files that you have downloaded through Google. I will talk about why it's hard to download them later, but let's say you have. Now you need some application that can read those PDF files. And you need some time and computing power to do this reading. What you do is, for each of the input that you have, each of the PDF files, you start the program that you analyze and measure its code coverage. Which kind of code paths the PDF causes inside the reader. You record them for all of the 100,000 PDF files, and then since you know, you can understand the difference between what code paths, what PDF causes. Based on that, you can reduce the number of PDF files in a such way that the finalized or the resulting set of the files causes the same code coverage as the initial set. Let's take an example. Let's say we have 5 files. One causes functionality A, B, and F to execute. Second one causes A, C, D, E, and so on. Now, if you look at those 4, if you only have you get the all files, because the rest of the 3 is just repeating the first 2. So you can already reduce the set from 5 files to 2. Now, how do you do it? How do you measure the code coverage? Well, if you have the source code, it is really easy. You have special compilers, or in some cases, compiler has even special flags that you add, and after that, the resulting executable, or it doesn't have to be executable, or XN sense it in other operating systems, but some executable that you the code coverage that is used. So with closed source software, one example or one really simple way to do it is to trace tree all the code. This is curiosity, tried it on my laptop in one VM. How long it takes so then you have some well, you have some a pin for that you can they do some additional stuff, but one bad thing about them is that not all programs run under them. You don't have such exact control, and you can't optimize them always that well as you can. Some third option, I wrote my tools for code coverage myself. I will explain how it works and how fast it works. Now, if you start code coverage on assembly level or machine level, you don't have to track each machine code instruction. You don't have to know. You need only basic blocks. Basic block is that doesn't have branching. So if the first execute until the basic block doesn't branch out or something like that. Of course, there's a special situation where it can loop out, break out from that. For example, access violations or some other exceptions that happen. But this is like separate case. So my first idea was to put breakpoint or write pretty much the debugger that puts breakpoint at the start of each basic block, and just record as the program executes through that. Now, how to get basic blocks? Who has heard or used a program called IDA Pro? Oh, cool. Some have. This is pretty much a tool that it's pretty much industry standard for reverse engineering. And what you can do with this, for example, what I did is combine it with IDA Python, which is pretty much a tool that you use to combine IDA with a Python script, scripting language. Write small script, so it recorded down each basic block from the executable or DLL file, and record only the relative virtual address from the base address. It means that for each basic block, it was recorded where it locates in the memory compared to the base address of this module. Either for testing it at the very start. Foxit Reader was used by me because it didn't need some extra DLLs. It handled only with the exe file. It was easier. It supports all DLLs and such, and I will talk about this later. It was okay of handling PDF files, and it had 611,000 breakpoints, or basic blocks where I put breakpoints in. I set it up, my fuzzer code coverage tool, in a way that if in last 8 seconds no new basic blocks has been reached, then it stops the work and tries again with new PDF file or new input file. Now, how much it took time for a module? It took each time when the program set up the environment, and then 30 seconds to actually execute it. So total 210 seconds, it means 411 runs per day, and this was kind of slow because I had much more PDF files to analyze. So how to speed this thing up? My first idea was that what is breakpoint in assembly or code level? It's one instruction, CC, and why not put it directly into executable? So back to the scripting. I now recorded still the RVA in the memory from the base address from the exe or DLL. But I also recorded RVA on the file. So where inside the file if it's in file system. Because if you map program from file system to memory, then it's not always the same. Because executable segments can be larger in memory than they are in disk. And I recorded also the original value of the first byte that I will be overriding. So, new process was like this. I first did the IDA analysis, record down all the basic blocks. Then I modified the exe and DLL in a such way that the exe itself already contained all the breakpoints that was needed. And then during the execution, I caught all the exceptions that happened, looked, is this exception happening because I added it to there? If it was, then I restored it into original value, so the functionality will remain the same. Recorded that this happened in this instruction point, and then moved instruction pointer back by 1 because I wanted to start basically. So second run, I cut it off 180 seconds. Otherwise, it's exactly the same. But now it took only 30 seconds, which is already 7 times better. Additional optimization that you can do at the really start was that I first downloaded 100 files, 100 PDF files, analyzed them, then took the best PDF file that caused the best code coverage of the files, and removed all the basic blocks that was by this one file from the list of the files, and then a list of the breakpoints, and then removed the changes in exe and DLL. So it was 60 times better than at the start. And I didn't have any more 611,000 breakpoints because the ones that were covered by this one file was removed. This doesn't make much difference. Now, how about the results? I downloaded 366,000 PDF files through Google. And the resulting set of the files based off this Foxit was 726 files. It contained the same functionality as all the 366,000. So the same code coverage was achieved with those 726 files as the original 366,000. Total code coverage based on that was 21.8% of all the basic blocks. Now, it might sound like a small amount, and maybe it is actually, but if you think about this, a lot of the code will be not covered because some configuration changes are not made. If you think about a program that has UI, you can tweak a lot of things from the configuration. And these all mean extra code coverage pathways. So either 21.8% is good or bad, I really can't say. And it took about 2 weeks. I think I had 3 computers running 10 or 11 VMs at that point. So, how large initial set you need to get as much code coverage as possible in this method? Graph in up area, it's pretty much what it's showing is how many files was added to the final set for each 1,000 files analyzed. And so you can see the graph went down quickly. But based on that, this graph, it's around 400 and 500,000 files, the limit would be reached. So best idea for PDFs with a Foxit reader, probably to download 500,000 files. But if I had 366,000 files, Google did it a little bit more heavily. Using similar method to analyze and find vulnerabilities in Adobe Flash. Then they downloaded 20 terabytes of Flash files, used 2,000 CPU cores, and reduced the 20 terabytes to 20,000 files. And did some fuzzing based on that. Now, these are little newer results. I did it again with PDF, with Adobe Reader, which should be better in understanding PDF specifications. Fixed files with Microsoft Word. For all of them, initial set was 400,000. And the final set that contained the same functionality, for PDF it was 1,200, for doc it was 1,300, and with docx it is 2,200. As you can understand, fuzzing through 2,222, it takes much less time than fuzzing through 400,000. Now we get to the fun parts. How to get those files. It should be quite easy. Is it readable? Yeah. Sorry about this. It's in Estonian. I'm from Estonia. But you understand what it's saying. It says that Google has 18 million files. Should be just start downloading. That's it. Nope. Actually, it says it has 18 billion, and it probably has, but it gives you only 500 top. So, what can you do? Also, if you say file type PDF, not all of those files are actual PDFs. You can have website or HTML file that has extension PDF, no problem. So PDF might not mean PDF file, it might mean just, well, you have extension PDF, actually it's file. There's also DDoS protections in Google. If you just with script start doing those requests against Google, then Google will block you, or actually ask block. So it's hard to download 400,000 files. So what was my approach? I used file.pdf AA, file.pdf AB, file.pdf AC. If I reached to ZZ, I started with AAA, and so on, so on. Since I started with file.pdf AA, I had a lot of anonymous alcoholics PDF with me, which probably shows something about me. But it worked. You could download with this. And since there's so many PDF files, so like for example, you what word is those? You shouldn't have those words a lot of in your sentences or documents, but since there's so many PDF files, you almost always still get like 500 responses for that. So you can download stuff with that. Problem with not being correct PDF files is actually really easy. At the start of PDF file, you have this magic number, %PDF. You start downloading the file, you check, is it %PDF? If it is, then you download the entire file. If not, then you skip it. And the third DDoS protection, it was much easier than I thought. It is based on timing. You just have to tune it correctly, because you just make a request, download files that Google tells you, and then wait for like half a minute, and then make next request. If you get the timing correctly, the DDoS protection doesn't execute, and you will not be blocked. It takes more time, yes, but since it's just running in some computer, that much. Fuzzing itself is that you move the input file that you have, the downloaded PDF file, or finalized set. With debugging attached, you usually have to write your debugger attached, and then you record if the crash or exception happen, you record it and move on, and do it again and again and again. What kind of mutations to make in those files? Well, most of my results are based on simple random bit flipping, just flipping randomly bits. This works really well, but also you can add stuff. For example, add long strings to cause some overflows. You can use some spatial values, take some byte and replace it with 00 or FF to get, again, usually some overflow or something like that, and such and such. About this, there's a lot of work done, so if you Google it, what mutations to make in fuzzing, there's a lot of information about that. Now about detection. Well, in most cases, when you're analyzing some executable file, you want to catch access violation exceptions. They are most valuable for you. Or dep violation. Dep violation is also very good. But access violation, pretty much what it means that some pointer in executable was messed up, and, well, pointing to in the memory that doesn't exist. So you catch it, you record where it happens, and you're happy. Also, I don't have some fuzzing, turn it on. If you Google it, you will get much information what it is, but this is really important of finding overflows and use after free vulnerabilities. What to keep in mind? When your application has ASLR, which most of the new important programs have, and you don't turn it off on operating system level, you have to just keep in mind that if you calculate or sort based on where the exception happens, which code is causing it, you have to take ASLR, you have to keep in mind that ASLR puts the executable into different memory locations each time. So the actual reason could be the same, but location where it happens is always different. Then there's random crashes. And random crashes are caused by something really unlikely that happened. But where it comes out is that your fuzzer says that, yeah, I found new crash. You run it, and it doesn't crash. And this happens quite often. Most problem with this is race conditions and such, in situations where, for example, you run out of memory, which is based on, you just happen, you run a lot of instances, and you run out of memory, but it is not usual situation. So the crash happens, but it usually doesn't. So for these programs, what I did was my script, if it detected a crash, it reran the same file again. If the crash happened again, then most likely it happened while testing also later. And you have to filter the issues automatically, unless you're extremely bored. When I was starting to fuzz Adobe Reader, then with first week I got a little over 1,000 crashes. The actual reason for those crashes were like 10 maybe, or 15 tops. But the crashes count was really high. And if I wanted to analyze them by hand, I would gone insane. So what you have to do is you have to do some addition. preliminary analysis based on the crashes that you detect. Your script or tool has to do it. And what I did was my script just filters results into separate directories. The highest level directory is near null, not near null, or both. Both is in some situations when crash happens, and when my script retries it, one happens in near null, one happens not near null. So this is for both. But near null means that the pointer that was near null, close to 0. So 0 pointer reference or pointer. And this is usually not exploitable. Usually. In kernel level it's different, but lately in kernel level. But 0 pointers are not that interesting for a security researcher. So those are usually ignored. Then in next level you have type of exception. Is it dep violation? Is it out of bound read? Is it out of bound, not out of bound read, but access violation based on reading, access violation based on writing, or so on. And then you have location of the exception, and if you want you can add also the stack trace, that what caused or what functions were used to reach to the crashing place. About each crash, what you need. For me, I always want to know what is the machine code or assembly code in the crashing location. So what was the exact machine code that caused the crash? Then what are the stack trace? So what was the functions executed before that? And then register values. What are the machine CPU register values? And if those are promising, then I do additional analysis. So if you find bugs, what you can do with those bugs? The first possibility, of course, is to inform the vendor. This is always a nice thing to do. Some vendors even pay you for that. For example, Google pays relatively well, but most of them don't pay anything. You can use CDI, which is Zero Day Initiative. They are a nice way of doing this while still earning some money. Because what they do, if they're interested in the bug, they will buy it from you, inform the vendor themselves, but since it usually takes time for vendor to make a fix, they will create the fix, not fix themselves, but the tool that monitors for this vulnerability themselves and sell it to their customers. So their customers are safe while the vendor is still fixing it. Most that Zerodium CDI base are not really great, but they're just okay. You can probably leave off of them. Then you of course have old approach to full disclosure, make all the world know, and make everybody either love or hate you. And then comes the really grey part. This requires some extra skill, that you can not only find the bug, but write the exploit that uses the bug to take over the computer. Now, those exploits have high values. Zerodium, I think a couple of weeks ago, that they will pay for an exploit that takes over your iPhone via web page. They pay $1.5 million for such a stable exploit. Of course, if you find maybe much less, but still they. Interesting possibility. Definitely, it's not white hat, but still, there's a lot of people who do that, and this is not illegal. Just for your information. And of course, you can write exploits for your own usage, not to attack someone, but for legal things also. For example, if you have pen testing, then you might want some exploits to use when you're testing your clients. So, since there are last minutes, a little bit about my tool. The fuzzer that I wrote is called Vanapagan. Don't use it. It's not the best fuzzer, let's honest. I just wrote it because I wanted full control over what's happening. There are better mutation-based fuzzers out there. But the main point of the talk, the code covers stuff called kavalants. This you might want to use to just reduce initial set of the file. There's also script for it's included with kavalants. So this is more useful tool. I don't say that fuzzer Vanapagan is bad because I found a lot of stuff with this, but they're better. Some information. Both of those have no real documentation yet, or I don't know if anyone loves writing documentation. He can contact me. And they're both developed as my own needs dictate. But you can branch out of them or use them on your own tools or such. I have no problems with this. One of the things that I will ask is that if you find something, don't tell me what you found. Just in case, don't tell me what you did with your finding, because if you sell it somewhere, it might be not legal. But let me know that you had any help from this program. It's just cool to know that your tool is helpful from someone. If you sell, then donate something. I, for example, donate 10 to 20% of my each finding that I sell to somewhere, and I sell only to CDI, honestly. But the reasoning behind this could be also that fuzzing needs luck. And donations, if you do them, they increase your karma. At least they should. They don't actually, but they should. And high karma increases luck, those who play computer games. So